So these are some fun problems in asymptotes. Okay, so some maybe problems in asymptotes. So last time we had discussed asymptotes, a little bit of theory and so on, but now there is no scope to go into much detail in the sense, yeah, let's go into some problems. So there is this problem which I had given last time. So this was as follows: show that a rational function, and if you would have seen the Wikipedia page, you will see that they have these kind of things. Okay, the Wikipedia page of this topic is very good. Okay, but show that a rational function has at most one um, certainly, yeah, so at most one horizontal, okay, or slant um, asymptote. Okay. And yeah, let's just try to prove this first. Okay. Yes. Yes. Rational. Exactly. Right. So your function is fx, right? And it's px by qx for some polynomials. So there is, so as long as you're not looking at vertical asymptotes, if you're looking at slant asymptotes or horizontal asymptotes, there is at most one. So first, just try to show that it has at most one horizontal asymptote. Okay, meaning that a tangent at infinity, basically. There can be at most one. And this can be a useful thing to just know even. Yeah, easy to prove. So, I mean, what am I asking for when I say a horizontal asymptote? Yeah, let's just focus on horizontal asymptote. Exactly, yeah. So you want a line parallel to x-axis, which gets closer and closer to this function as x goes to infinity. And well, a good way to say it is that it is a tangent to the function at infinity. If you're willing to put in infinity, then the language becomes uniform, just like parallel lines meet at infinity. Or another way to think about it, and these are some, yeah, is that this function behaves like a line. It means behaves like a the y behaves like almost like a constant, yeah, and then x goes to infinity. So that's another way to see it. I'm not writing these things. Yeah, it behaves almost like a constant. Yes. Mm-hmm. Okay, so let's just focus on the first case first. If degree of p is bigger than qx, then what happens? Yeah. Uh-huh. Okay. Let's say limit x tends to infinity. Okay, so writing this as small, or maybe, yeah, so that should have been gx anyways, plus rx. Y tends to 0. No, degree of p is bigger. Rx, sorry, yeah, you're saying Rx, right. So Rx by Qx certainly, so let's break this up. Plus Rx by Qx. And you see, we can, if we, I mean, assume that the limit exists, or even if the limit is infinity, it's not an oscillating thing, so you can just separate the limits. Okay. Okay, so no, even if it goes to infinity, I mean, one cannot say that there is no hope. Okay, as far as horizontal tangent is concerned, maybe no. But okay, let's try to say it more formally. So, right, so we can forget about this thing. We can forget about this thing, and so this becomes limit of gx as x goes to infinity. Yes. So you are just calculating the limit directly from here. Okay. So then let me just write the first few terms. Yeah. So let's say an x to the n plus an minus 1 x to the n minus 1 dot dot dot. In the denominator, it could be some, let's keep bm only, bm x to the m plus bm minus 1 x to the m minus 1. So then you're saying divide by the highest power of x. Sorry, I mean highest power of p. Right. So, but then, so then what happens if we do that? Then you get an. Sorry. Uh, right. No. So yeah, right. M is less than n. So yeah. So I mean, yeah. I mean, if it is, if so, if the degree is no, but see, our goal is to not just check if the limit is infinite or not, right? That is not sufficient. You guys see, we have to check for asymptotes, right? That is the difference. So, but so here, just give me a minute, okay? So n, so if you divide by n, so then this becomes m minus n, and this thing goes to 0. No, so this is, oh, next to the power. So when x goes to infinity, yeah, this goes to 0. So then it goes to infinity. But just because it goes to infinity, so if the limit goes to infinity, then what can you say? So limit, so this case, so by both the method, this case gives us that the limit goes to infinity or equals to infinity. Yeah. So what can we say about horizontal asymptotes from here? That's all. Let's first answer this simple question. Both of, sorry, no horizontal asymptote. Yeah, is that clear, Adish? Is that okay with you? Yeah. This implies no horizontal asymptotes. Yeah, is it okay? Is he here? Is it okay? Yeah, follow. Okay, good. All right. And one can just check it from the definitions, right? Because having a horizontal asymptote should mean that, so if there was a horizontal asymptote, then the limit of this, you could say, so if the horizontal asymptote of y is equal to c, then the limit of this divided by, or yeah, divided by c should be equal to 1. But obviously that's not possible, yeah. I mean, if c is not 0. Okay, so this is fine. And the other things you guys can do similarly. So let me not complete the problem, okay. The other cases you do similarly, but there is some work to do. Okay, you cannot just say empty case. So please complete. Because it's that we have done the easy case. Let's do, no, let's actually, I'm sorry, yeah, let's actually do it, because then that's just, we have not done anything in this, yeah. So let's do the case in which the degree is equal, yeah. So then what happens? Exactly, and that's a unique horizontal asymptote, right? If degree of P is equal to degree of Q, then that implies unique horizontal asymptote. Okay, and then what happens? Okay, so let's okay. So then what happens if degree of yeah? Let's not rush. What happens if degree of P is less than degree of Q? Yeah, this implies that y equal to 0. So we are just making the interpretations. Okay, there is nothing really we are doing. Yeah, y equal to 0 is the unique, and that's the only one. You can just, if you need to write it, you can say that if there is some other c, then it's clear. Unique horizontal asymptote. Okay, so there is really no problem. But let's actually go to the other things. Let's go to the slant asymptotes. Okay, otherwise it's not good. So let's again. Okay, 1 minute. This is a new thing, so the keyboard is different, and I don't use the laptop much, so confused. Okay. So now let us investigate the slant asymptotes. Okay, we are doing these preliminary things. Okay, so slant asymptotes. Yeah, so you guys please try to say. Okay, fx by mx plus c. Yeah, you can in fact just say 1. Yeah, right. Okay, so then what's the condition? So can you tell me directly the condition on degrees? That's where it will go. Right. So that's a straightforward thing, right? So this implies, or rather it is if and only if, right? I mean, this will only happen if the degree of px is equal to degree of qx. So the degree of qx plus 1 should be equal to degree of px, right? Yeah. So this is just simple. Okay. So you can see, I mean, and once again, you will. Okay. So then why is it like why is there a unique slant as in why is there a unique mx and c? And how would you find it from px plus qx? Yeah, these are the questions that are remaining, right? So why is there unique and how would you find it like in a easy way? So you're using this condition, yeah, right? So x to the n plus x to the n minus 1. Okay. Right. Right. So from here, how would you show uniqueness and how would you? Okay. Okay, then. Yeah. You can just compare the highest powers, right? So that's good, yeah. And you can actually then show that it's coming out to be there is just a unique choice, right? Or you can simply just divide px by qx, right? Then you will get a linear polynomial plus something like rx by qx. This goes to 0, and this linear thing that you will get is your is the asymptote, right? Okay. So this is rather not very difficult. So okay, I mean we are doing this simple stuff. It's fine, not a big problem. Um, okay, now I want to find asymptotes maybe of some more interesting curves, right? Some more interesting things. So let's see. Let's. So this is another example which I'm taking. So finding, now we are going to do like finding asymptotes. So far we were like finding asymptotes of functions. Yeah. Now, but it's a geometric thing. So we'll try to look at other geometric things described by equations and finding asymptotes. Let me just say via implicit equations. And it is not a very technical thing. Okay. It's, using your intuition and the definition, both clear definition and intuition, and just working it out via implicit equations. Finding asymptotes of curves when they're given in the implicit form, sort of. So here is what is given. There is x square plus y square equals x square y square. Yeah, and we need to think how we can find the asymptote of this. Okay, so just think. I'll just be back in a minute. Okay, so you see, point is that this is a geometric figure, right? It's a geometric figure, so asymptotes make sense. We have not described very rigorously what asymptote of this kind of thing means, because our definition has depended on the y coordinate being isolated depending on the s coordinate. But still, you can understand what I mean. So let's try to find it. Okay, so just think. I'll Okay. So any ideas? By the way, let me just interrupt and just 1 second. Let me just interrupt and ask one. So I mean, at least maybe tomorrow or Saturday or Sunday, is morning time possible for anyone, for all of you? Because there are holidays, and any morning time Saturday, is it possible for, okay, for Chandan and Adish? And because morning class will be much better. Okay, Saturday, Sundays out of the way. Okay, good. And Chandan and Raghav, like, because it will be much better class, you will see somehow. Because right now, I mean, I'm okay, I'm taking the class, but it's much better if you can. Okay, so Chandan, Raghav, is it okay with you Saturday morning at least? Saturday morning is okay. Try to do, you will see the difference. And good. So at least Saturday morning we can do. So Saturday morning, and how is tomorrow morning? Yeah, I mean, if you're willing to attend, if because right now we already, okay, forget about tomorrow morning. Let's do on Saturday morning. Okay. Yeah, Saturday morning we can do. So morning mean like we can do at 7, or if that is too, you can do at 8. 8 is fine, I guess. 8 is not too early, right? Yeah, 8 to 9 we can do. It will be very good. You will see. Okay. Okay. So okay, I don't have any problem. I can do my other thing. Then I wake up at around more before 5, before 6, not before 5, before 6. And but anyways, yeah, fine. So we'll do Saturday 8. Everybody should be there. We'll do 1 hour class. It'll be good. Okay. Okay. Cool. So let's continue. Sorry, y square. Oh, okay, you actually solved it, but yeah, but then it's still not a function, right? So yeah, you will have to take cases and do, and it's a little complicated that way. I want to see, yeah, yes, Adish, you say. Okay, right, right. Obviously, that's right. X is sec theta. Uh, Parametric equation. Yes, yeah, good. Uh, I mean, yeah, basically you have described that figure using a parameter, not so the parameter is not the x-axis. Now you have a different parameter, right? I mean, so what Raghav you have done is fine, but then you become a little complicated, two cases and then what regions and whatnot. It can be done, but and it certainly is okay. But I want to emphasize on this method because this is a mixture of some substitution thing and using parameterization parametric form to find the okay. So okay, so now this is the curve. No, why it has to be greater than 1, right? If it's less than 1, then 1 by x squared becomes greater than 1. These are all real values. From the second equation, it becomes obvious that it has to be. Right? Now, how do we use, this is what I'm trying to emphasize on. How do you use the parameterized form to find the equation? Uh, sorry. Haha, okay, that is okay. That's a minor thing. Anyways, let's forget about, yeah, that's right. But substitution is fine. Right, every x and y can be captured by this kind of theta, by this thing. Okay, this is perfect. Yeah, that's right. Yeah, little bit. The modulus has to be less than. Yeah, this is fine. This is perfect. You know. Now, how do we find the asymptote? So let's say let's do it so that we do it a little. Let's say y equal to mx plus C is an asymptote. Any idea how this curve will look like? That's also a good intuition to have. So you have already said that x and y have to be greater than the, meaning that you're saying the magnitude has to be greater than 1. Yeah. So obviously things will be outside. Goes like what? It is. Um, is it like 1 by x? Why is it like 1? But why is it like it might be correct? Oh, no, it's a huh. Ah, yeah, like this you're saying, and then you're okay, and then you're saying it will be like this. So you see, once I mean, even from the figure now, you've already found the asymptotes, I think. Sorry, say that, say that. Huh. Yes, yes, yeah. So those are, and also the minuses are there. So you have to see. So those are the, yeah, yeah. Right, right, right. And there are no slant asymptotes, it seems. Okay. So Chandan, is this point okay with you? Right. So it's not like a technical solution. It's not a rigorous solution, but you see, this is a nice, yeah, nice. But I want to emphasize, how do we, like, given the, okay, if you throw the figure, it is nice. But if you have a parametric form like this, then how do you find the asymptote? Like a little more formally. Yes, yes. Even in the subjective, if they are not like, depends, but it's okay. But you need to have this method, because if it's more complicated curve, then some, round and going, some it can. And sometimes the answer would be no asymptotes. So you would also have to look out. Like if the curve is bounded, like if the resulting figure is bounded. Why not? If it is secant theta, no, no, you cannot do that like that. I think because it's not a function. It's not the graph of a function, right? That's why you cannot do it like this directly, right? The situation, if you want to look at more cleanly, the situation is a little bit like this. T going to ft comma gt. I mean, t goes to ft comma gt. And you may get a, and we had seen a little bit of this last time. I think we had seen a very interesting example last time where we could find the, I don't remember the example, but we could find the, now it's a very, it could be a curve like this. Some pattern hopefully will be there like this. And then you need to find the asymptote. So, so obviously as t goes to infinity, then how do you find the asymptote? X by y is equal to sec theta by cos theta, cos, yeah, that's tan theta, right? Right. So yes, that's what we had done last time. That's the wrong non-rigorous thing that we had done last time. Right. So it is slightly non-rigorous because you see the tangent is actually not on the tangent is not on the curve. It is not exactly on the curve. Um, right. So how do you say this? How do you convince it in a more rigorous way? Must correspond to some. But that's on the curve, right? But when you substitute this x by y equal to tan theta in the line, that's not good, right? I mean, you see, that's not completely rigorous because the line is not on the curve. But the asymptote is not on the curve. But I mean, you can still do it. And if you take some case like non-vertical ke liye, you have to do something else. It is fine. It's but that you can do. But let's see. Someone should try to give a reason or find an alternative. Okay. So think if you find some way, you have to take some time and think. It's directly. Hmm. And that turns out to be correct. But the point is that this is not a rational function, right? It is a y equal to square root and it will become square root actually. But yeah, I understand. I mean, the fact that it has a rational asymptote will not change. But then you have to then go into try to explaining why that happens. Okay. So, I mean, here also we can do a similar thing. Let's see. So there is one way which I think one can think of is let's just focus on slant asymptote. Yeah, and we will actually see that it will be a slant, meaning that okay, let me just say non-vertical, non-vertical. If you're looking at non-vertical asymptote, then what can you say? You can certainly say that x goes to infinity. All right, as x goes to infinity. So let me write that in word first. as x goes to infinity, this cosec theta minus this mx minus c, this goes to 0, right? Because that's on the curve. This is the values on the curve, points on the y values on the curve. And these are the y values on the line, right? They go to, for the same value of x, they go to, the difference tends to 0. But yeah, so that's where it's a little bit, x is secant theta. Should we? Yes, right? We can take that. Yes, that's just the input we are taking, right? X is, because that's how, those are the values that are being taken, right? So we can then say this, that for the same value of x, for the same value of x, right? The y value of the line and the y value of the curve. It's a simple thing, but still, because it's just the, we get confused as to is this rigorous, is this right? And that's the why we are doing this. And we want this to go to 0 as, so what should we say about theta now? Tending to pi by 2, is it fine? Pi by 2? Yeah, you can say maybe. Okay. Right. No, but then sec theta will not go to infinity, right? Oh, we don't have to worry about cosec theta. Right. Or am I, no. Am I saying something wrong? No, it's right. Yeah. I mean, we want to make the x go to infinity. That's our goal. So this is okay. Then what happens to cosec theta? Yeah. Goes to 1, and minus c goes to 0. I mean, so it's a constant. So this means the c has to be 1. Right. And then did we get that m has to be 0? Oh, yes. Yeah. I didn't even, how did I just forget it? Right. Yeah. So this limit has to exist, right? So 1 minus c minus m sec theta goes to 0 means that this goes to infinity. So this m has to be 0. So you see, we are getting both the things quite rigorously. Minus 1. Yes, yes. So yeah, that's right. So theta going to pi by 2 is one way, but then, theta can go to 3 pi by 2, and you can work that out. That will be the other. And similarly, you can work out the vertical asymptotes, right? So in the vertical asymptotes, you have to just let x go to some constant, and just and let y go to, and check when y goes to infinity. Yeah, that's just on the, you don't have to consider a line if you just do that on the curve on this. So that's fine, that can be done. Okay, so it's okay, right? Simple things, but we have to do it. By the way, so for a rational function, where are the vertical asymptotes? We didn't discuss that, but just asking, like quick question. Right, exactly at the places with the denominator. So the roots will tell you. So at most, how many vertical asymptotes you can? Right. At most, right. So then those are some simple things. Right, but I wanted. Yeah. Uh-huh. Right. Sorry. Yeah, the GCD, we assume that the GCD is 1, right? then only, sorry. Huh? Yes, right. So we should, when we are looking at rational function, yeah, otherwise it doesn't work. No, I mean, you could still have vertical asymptotes. No. So the vertical asymptotes don't. So sorry, the vertical asymptotes will not change. Yeah, even if you, yeah, because only those zeros which are only in the denominator, not in the numerator, they will correspond to vertical asymptotes, right? So the vertical asymptotes will not change. Right. Uh, Sorry. Haha. X plus 2. Yeah, this is a rational function. Yeah, it is. Yeah, it is a rational function, and it is not the same. But the point is that this is not the same rational function as x minus 2. These two are different. Okay. As strictly speaking, as functions, they are different things. Okay, because obviously at minus 2, one is not defined and the other is defined. Okay, but they're going to have this, but they will have the same vertical asymptotes. Okay. So actually in the parameterized thing, I wanted to discuss a different method, but let's not go there now, leave it. Maybe, yeah. Now I want to come to a more general question. So if I can get some example, it will be good. One minute. No, so I don't get any example. Not here. I had given an example in the test, but anyways, it doesn't matter actually. So now we want to find asymptotes via implicit equations, but now we want to do it for things for which we cannot even find a parameterization. Okay, I mean maybe you can find, but let's say it's difficult to find. Okay, so you could have something like this maybe. Okay, and so you could find a parameterization for this, but this is a simple example I'm trying to do. X square y square, let's say this equals to 0. Yeah, I mean this will be some curve, right? But yeah, 1 minute, so just give me a minute. um yeah, fine, this is okay. Just checking that whether it's actually unbounded or not. So this is fine. So this is just a curve, right? You have to draw something, and then how do you know the asymptotes of it? Okay, so how do you find asymptotes of this equation? Meaning that the set of points that you'll plot which satisfy this equation, how do you find asymptotes? Like conic sections, right? Hyperbolas, and but for them we have parameterizations. How do you find asymptotes of these kind of things? This is really the question. Yeah. Oh, so you're saying some factorization, right? But okay, so this is me a minute. So I don't want to, uh, because that is not the point of this question. I mean, you could factorize it, but just give me a minute. I'll take out that paper. No, it's 7, I think, or before that. I could put anything in the here, but I don't know what will happen. So where is it now? It's not here. No, so I just want to write anything, like maybe a 5-degree equation. We can write. We need to think about a general method to find asymptotes. So we can't even plot this, right? Y equal to 0 and x equal. Okay. Y. So why is this? Yeah. Okay. So let's see. So you're saying putting the coefficient of the highest degree of x equal to 0. But why? Uh, no. So you're saying y equal to 0 is a tangent. Sorry, is an asymptote. Why is it an asymptote? So you're saying because you put x equal to 0 and you have solved, you've got y equal to 0 as a solution. So what is the technique? Yeah, so let's go into that. So what is the technique? Put the coefficient, but okay, so in this case, you mean you'll put this equal to 0, but that's just 1. Okay, so you're saying this is the coefficient. So you're writing it, so you're saying that you want to write it as a polynomial in x. Okay, so let's see. So you write it as a polynomial in x. No, so then I will write it like this. Let's try to explain this method. Seems interesting. Though it will not always work, I'm quite sure, but it will work in most cases. And so that's good enough, I think. Huh. Okay, so this method, wait, so here when you do, so here you get that y equal to 0 is an asymptote. Okay, so this, so um, so this way we can find everything except for horizontal asymptotes. Sorry, no. So this is certainly a horizontal asymptote, right? Right. And so you're saying that by this method you will get the slant asymptotes also, Uh, or only or so this is only horizontal asymptotes you will get. Yeah, just do it with the x and get the vertical asymptote. So then what is the intuition? Like, why does this work? Yeah, so this is, so we are saying that when x becomes very, very large, then this the set of points on the curve behave like y equal to 0. I mean, the values of y don't really change and they are around 0 and they don't change much. So the technique is, yes, said the technique is to, you have your, so this technique is only to find horizontal asymptotes. Okay. You take your algebraic, you take your two variable equation and you write it as a polynomial in x. Okay. Then you look at the highest power of x and you take the coefficient and put that equal to 0 and solve for the different y's. So suppose if you had something like y square minus y x to the 4 and others lower powers of x. So first writing it as a polynomial in x is important. Then you can solve for this and get that this will imply that y equal to 0 and y equal to 1. Both are possible. Both are asymptotes. Chandan, is that right? Yeah, the both. But then what is the explanation? So Adish, you do get the method? So, okay. So, but yeah, so this is the way to find horizontal asymptotes. And similarly, you can find vertical asymptotes. Slant asymptotes, maybe you have to do something else. But then, okay. Yeah, but then why does this work to find, yeah, to find the horizontal asymptotes? Any ideas? No, x goes to infinity. That's all. Hmm. That's right. Right. Okay. Hmm. Okay. Right. So let me think. So all of you guys, I think. Yes. Yeah. So you write your curve, two variable curve, as a polynomial in x. You take the highest power of x. You take the leading term and you take its coefficient. Now its coefficient need not be a constant. If it's a constant, then there is no horizontal asymptote. But then you take that leading coefficient and it will be a polynomial in y. You solve it and find the roots. And those will be your horizontal asymptotes, means y equal to those roots will be your possible horizontal asymptotes. Right? Like in this case we just had y. So this equal to 0 means y equal to 0. So that's a, but if it's y square minus y, then this gives us two possibilities, y equal to 0 and y equal to 1. So, well, both, I think, yeah, method tells us that both will be horizontal asymptotes. Just a minute. Yeah, the point is that these are not functions. So it's a little, so it will always be a little non-rigorous because we in fact don't know the exact definition. Right? There is no exact definition yet, right? What does it mean to say? But just give me 2 minutes. I'll form a reasoning. Huh? Right, right, right. So you're taking x. Huh? Yes. Right. So if you have a py x to the power, let's say 4 and some 3 and some other things. Right. So I think, yeah, that's perfect. Yeah, I should have thought of that. That's right. So then you divide by the highest power of x and you get py, and then you take the limit as x goes to infinity, right? And because this is an equation, so that's a good thing, right? It's an equation. Everything is an equation here, and so on. So when you take the limit x tends to infinity, you are saying that these terms are going to go to 0, right? This qy, I mean, they look like on the surface, but the y and the qy can change things, right? That's a slight, because you don't know what is the resulting values of y, you see. But still, I mean, if we argue that, then it is right. Yeah, then for this limit to go to 0, py must be 0. Any y that makes that py 0 will make this work, and those will then be, yeah. Then for those values of, no, for those values of y, this will go to 0, right? And then, yeah, then those values of y will correspond to it. But the thing I was thinking, because there is a qi thing, right? Yeah, we don't know what y is. That's the poor problem. Yeah, because when you take x goes to infinity, then the y can, that's the problem with this reasoning. Yeah, I agree. That is a problem. Yeah, that's right. So that's why this is a, but you see, in a certain situation, this may be that the other lower powers have constant y's, and the qy's. So the coefficients of the lower powers of x, if they turn out to be constant, or if you can understand them, then it is might work. So that is okay. But then what I was thinking is like, see, you can look at this um, no, so that doesn't, it's all vague. Yeah, that's right. Because we always give these vague reasonings. 1 minute. So when, okay. Uh-huh. Right. Right. Yeah. All the other coefficients of x, powers of x, there, y, those will be good. If you assume that this is a horizontal, there is a horizontal asymptote. Yeah. So if you assume that there is a horizontal asymptote, then these must be the possible horizontal asymptotes, right? The roots of py, the roots of the highest coefficient of x, the polynomial in y, they are the possible horizontal asymptotes, right? There is no other possible horizontal asymptote. Yeah, but not all of them might be. That is the problem. Yeah, right? So they are the possible ones. Yeah, and to find all of them is not so, to find exactly which ones of them are not, that is I think that's a little beyond. So usually, we'll say all of them are. Okay? There is no problem. Yeah, that is fine. The reasoning I was thinking is because this quantity is 0, so because this quantity is 0, as x goes to infinity, so as x goes to infinity, this quantity is almost equal to, but that's the same as this quantity, right? I mean, this thing is almost the same as this thing as x goes to infinity. Does that look correct? But that has the same problem, right? With the y. Yeah, so that's the same problem, right? But yeah, that's as far as you can get with the non-rigorous thing. Yeah, to make it rigorous, uh, one has to make some definitions. One has to basically see this. So this curve is lying in two-dimensional space, right? This curve, yeah, yeah, huh, huh, right. You may or may not get roots, yeah, if you're looking for real roots. Uh-huh. Right. Mm, some roots must remain the same. Um no, that's not correct. Or no, that's correct. Yeah, that's correct. Sorry, that's certainly correct. Yeah, yeah, but you cannot plot it. I mean, you cannot. No, so that's 1 second. So theoretically, it's an XY plane, but But you're saying common roots. No, but as the values of x changes, then the roots already change. You're saying if you want to get the same y again and again, so no, because the y of the value of y can constantly be changing, right? You are kind of saying that the values of y don't change much. I mean, they remain almost. Right, right. But it will not satisfy, no, it will never satisfy in the finite plane. Yeah, means the values of y that you get will get closer and closer to zero. Means you will always get values of y for when x becomes larger and larger. You will always get values of y which are, you can get other values of y also, but you will always get values of y which are closer and closer to zero. Yeah, that you can say. Yeah, that's right. Okay. Yeah. So okay, we have explored these things. Let's not go in the rigorous thing, but let me just say one more trick with which you can find all the horizontal, all the asymptotes at least. Yeah. So the point is a similar thing. You take the highest polynomial in this. That means you can write this in terms of degrees, right? So you see these are the degree 5 terms, or in fact there are 3 of them. Sorry. So these are degree 5 terms. So let's forget about the second equation now. And just similar vague reasoning, right? That this will be the dominant part. So you take the dominant part, right? And you solve for this. Now this can be solved for, right? So you take, I mean, at least theoretically, it's a, okay. So why I'm saying this can be solved for is because of this. This is a homogeneous, right? 2 variable. So you can divide by y to the power 5 and you can solve for this, right? Because it becomes a polynomial in xy. So basically, see what kind of things you will get is a1x plus b1y, right? Then you get a2x plus b2y, and you will get like this, right? So the point is that these things, right? I mean, you see, right? I mean, this curve will be dominated by that largest degree portion, the largest homogeneous component. And to make that, so now you want to make that 0, to make that 0, I mean, we need to move along one of these lines, right? At least in that direction, right? We need to move in one of these directions, right? And so your lines will be ax plus byi plus some ci which you have to figure out independently. It's not coming from here. You have to figure, and that you can figure out. That I suppose it's not very difficult, right? Once you know that this is the slope, then you can figure out the ci also by some, maybe dividing by something and so on. Yeah. Means you just take the ratio of this line and that equation, and you say that that goes to you could no, but yeah, you could just say that that goes to 1 as x goes to infinity, and that way you can figure out the ci, right? So that's not a problem, but this is the thing. Wait, but then how do you so how do you figure out the ci? It's not very clear. 1 minute. So let's just see. Let's take a smaller, or why don't you guys think about it, right? But think about how you would figure out the ci. So if I tell you that these are the tangents, because I'm just running out of time a little bit, that's why I took the class early, to do something else after this. So this thing, these are your slopes of your tangents. Now how do you figure out the ci's is not, okay, so it's not at all difficult. You try to find it, okay? And then maybe next time I can take 5 minutes and explain the more rigorous way. The point is that you put another variable, and this becomes a equation in 3 variables, okay? And so there you can, like, intersecting at infinity, you can actually get those points, okay? So anyways, we'll see that next time, or maybe we'll not see it. It's not very, yeah. Okay. So these are the things we learned today. Yeah. Okay then. Thank you. So yeah, let's see. Maybe we can meet tomorrow night, or if not, then definitely Saturday morning. I'll send a mail. Okay. And tomorrow we can. So what topic should we do? Should we solve the paper? Because the